Yeah, and that's one of the big things is a lot of times you think that you're doing things right and you think you know what you're doing, but until you have to verbalize, write it down, and then share it with someone else and compare, you don't realize that there's actually a disconnect there that you didn't notice in the first place. Aaron?
I also did it for myself, and I thought it was pretty helpful. I also spent a lot of time talking to my cats and my wife about it, which was super helpful because I'd start off thinking one way and then later, come up with different information. So I feel like even if you don't have other people to bounce ideas off of, just saying it out loud if you're stuck doing it by yourself is helpful.
Yeah, which is why I think I felt okay offering that option for people to do it by themselves. You might Google things and see how they relate to each other or where they're used. You might fact check some of the stuff. You don't have to take everything that I hand out as fact. I might, kind of fun maybe, and I should do it. Intentionally put some stuff in there that's false and see if you guys pick it out. You guys should be able to problem solve, right? And you're scientists. That's why every single time I send an announcement, I say, Dear Scientists. It's because you guys are fact-checking, evidence-based scientists, and that's what we're working on, developing those skills in this class. All right, so today's class, we are going to build off of what was done in the supplemental instruction by taking some of those things and thinking about what that means for solutions when you have mixtures and not pure samples, but we did some of that in that activity. If you have lab, have you guys all figured out the resource, the most important resource for your pre-lab quiz? Two things you need to do before lab. One, read the procedure in the background for it. You're going to have to use appendices because you might not know everything that's listed in that, right? So your TAs have probably already told you about this. So there's appendices in the back. How to use a volumetric flask. You might not have ever heard of that word before. And in the back of the lab manual, there's a tutorial there of how to do that. There are also pre-lab quizzes, which the whole point is Dr. Belford, I'm going with the flow, I'm doing what he suggested. Dr. Belford said that he basically wants you guys to be able to have heard of things that are relevant to the lab, to be able to go and find equations that you need or definitions you need, and then that will be on the quiz. So the pre-class quizzes that he has posted online are an algorithmic version of what you're going to have in the quiz itself. So you got to take a note card with you. You all know about the note card? You got to take a note card, handwritten front and back, I guess, with equations, examples of problems, whatever you want. When you go in the lab, you have to know, basically, know where to look to find the answer and to find the way to do the problem. And then we're going to use those concepts in class. So if I were to go, maybe I'll pull it up. Actually, let's do, if we go into our black note, not that one, back, into our Blackboard course, I've actually made a link directly to it. This lab resource is right here. If you click on that, these are all the online version of the appendices that you have in your lab manual. This lab prep quizzes, this is what you should absolutely spend some time with before every single lab. So today is experiment 2A. There are all these quiz questions. And so this is what your pre-lab quiz is going to be at the beginning of lab. So if you don't know how to figure out the percent mass of Ki in the solution, then you click on the hint. And then the hint pops up a little thing. You need to figure out what they're doing, what these things mean, and then you'll pass the quiz. You just write these things down is how Dr. Belford wants you to do it. We'll try for a couple weeks. If it's absolutely terrible and it doesn't feel like it's being useful and prepping you, at least knowing where things are, I'm willing to consider at least for, actually I can't do that, can I? Because all of our labs are intertwined. Yeah, we'll figure out how to make sure it's optimum, but I don't know how much flexibility I have in that. Do you guys have a clear understanding of how to use this lab prep page? Echo?
So that's what we'll be using when we get into the lab?
The concepts of solution chemistry, for instance, today you will be using, and you'll be doing some measurement, and you'll be doing some pouring, and you'll be doing some calculating. So yeah, so the idea is that this stuff, it's not the typical way I'm used to a pre-lab quiz, is if you've read the procedure and understand it, that's what the quiz is about. These ones, the way Dr. Belford has described it, is not. It's more, what are the technical skills and concepts that are going to be applied, not just the procedure. So there'll be one or two questions on the procedure, is that right, guys?
I think there's, not this week, I don't think. I think everything is centered around that this week.
Yeah. So if you can't answer these questions, then open the hint and figure out, it shows you basically how to do it. For this week, I intentionally helped you guys out on this. We are not really planning on doing concentrations in class today, but your pre-class quiz was on that, and we'll have a little bit of class time devoted to that. Peter?
I would like to revise my statement. There is a procedural type question. It's a situation that's set up that's similar to procedure. So they will have to be aware of that. So there is, I guess, in a way, a procedure type question.
So the way I understand it is there'll be a little bit about the procedure, but most of it will be about either the math concepts or the application, whatever it is from that quiz prep site. Okay? That is the way it's going to be going forward. So let's try to get on the same page. Make sure you study that before you go to lab. At least today you'll have some background with some calculations because you did the pre-class quiz. All right. So we're going to finish talking about solutions in IMFs. Everyone get a chance to read this question? I don't think it's on your handout today. I have 42 responses.
Oh.
I'll wait for another 30 seconds. Couple more seconds. All right, I'm going to close out. Did everyone get a chance to compare with someone next to you? Whenever we're doing this? All right, so we're kind of split between two answers, response 3 and response 4. So 3 and 4 both say liquid. How do we know it's a liquid? Can I hear from a volunteer? We have the same 3 hands. I appreciate that you guys are willing to share your answers. I want to try to hear from as many people as possible. So if we can hear from 2 people. Angel?
It's above the freezing point and below the boiling point when you convert it to Kelvin.
Of ethanol. So you looked at the table and you said that ethanol is right here. We have the boiling point and the freezing point. How do you know it's between those two? 321 doesn't look like it's between those.
That's in Celsius, and 0 degrees Celsius is 273.15 Kelvin.
Great. So that means that we have around 50 degrees Celsius. Is that right? 48 degrees Celsius. Okay, so we need to be able to convert between those. And then we see it's between these two, so we think it should be a liquid. And basically what we're going to try to do in the first half of class is answer between 3 and 4 to try to really understand what's going on in the molecular level of those samples. So we'll be coming back to that. So my goals for today is to have you be able to draw and interpret a heat curve, draw an appropriate scale.
What was the answer?
We'll come back to it. You will be able to tell me shortly what the answer was. I want you to be able to describe from a molecular perspective. This is really important to me. The molecular perspective of what happens during heating and cooling and phase changes. Predict how the vapor pressure, remember we talked about the pressure last class, how that changes based on the strength of the intermolecular forces and the temperature. We're going to relate concentration, some stuff that will be useful for your pre-lab quiz. Calculate molality and mole fraction. I will need to keep on track to make sure we get there. And then here's another link to the pre-lab quizzes. That is also linked through your lab Blackboard page, I believe. Also, you can just Google Belford and then navigate there. But our Blackboard homepage, I think, is the easiest link. And Chapter 13.1 has those calculations, as well as a ton of other YouTube resources I'm sure you guys could find that will help you go through those if you are not doing it right after the class. I've also put up a couple things here that I think will be really useful for exam practice, if you get together with groups of people and study for the exam, it's never too early to start studying. I think we have about 2 weeks until our first exam. Does that sound right? 2.5 weeks? Yeah, it's the 22nd, maybe, of February. So the idea is all written out here. I'll post the slide. You guys can go grab this. I want you to pick a molecule in the notes, footnotes of this. There's a ton of different molecules. I want you to write what do the molecules look like, that different shape, different temperature, how do they interact with each other, maybe even drawing out the molecules and showing the interactions between them, and then comparing it with someone else, and then grabbing a second compound and doing kind of a practice thing. So I'll leave this all up here. I just want to let you know that I have some suggested things you can do to practice. Bring them to office hours. That'd be awesome. All right, so the first part of class is going to be spent working on the first page and a half of your worksheet. We have a heat curve. It's for water. It's kind of a cartoony version. I want you to take 1 minute and look at the heat curve and try to describe to your neighbor what it's showing. We're going to get together, make sure we're all on the same page for that, and then I'm going to have you answer all the questions, okay? Are we out of there? You're going to take mine? There should be a stack back there too. You want to grab those? Back behind Peter? There are 55 of Alright, what do you do? Well, this should be on different pages. 3 pages of water, or it might be the synthetic captain cells here. And then that's 2 really strong words. It's rough.
My question is,
So I think we're going to have a couple minutes.
I'm so confused.
All right, let's get on the same page. So if we're looking at this, can someone describe in a sentence, without talking about numbers, what this graph is looking at describing? And I think I'm going to try to implement a rule. Everyone gets to talk once during class. How's that sound? That way the people who like to talk can talk. You just got to choose when to talk and share your thoughts. And then we'll... So Jonathan, do you want this to be your one?
No.
Okay. Echo?
It's showing the different states of water with temperature change.
Okay, and can we add something to that? What's another really big component? Yes. Say your name again. Shinidra. Great. Great. So really huge component on top of what Echo said is that heat is being added, and we have a temperature axis. And that might miss one little itty-bitty component of it, but that's what the questions will get us through, okay? So we start with what state? At the beginning before we add any heat? Solid. We have solid, and the compound is... What molecule is it? Water. Okay, so it's solid water, it's ice. We add heat, and then we follow the line, shows us what happens to the water as we add heat. Okay, so go ahead and start working through those questions if you haven't already. Be very specific in your answer and look at each individual component, okay? Make sure you pair up with someone else. Bounce ideas off them. I don't want to see anyone sitting by themselves, please.
Adding people to
Yeah, it takes a while.
very simple. See my 4-year-old.
So how does this one turn out? The temperature is going to be, it's going to be.
I said we'll stay at 0 for a bit. Jason said it.
Okay, and that's or within each one day.
Yeah, right? Yeah, close money right now.
Once you reach self-satisfied, unless you change
Raise your hand if you want another minute or two to get to question number 11. Okay? Try not to be too specific in semantics, but make sure that you understand the concept and put something down you think is reasonable.
You want to start writing intermolecular forces, but it's also mission possible. No, possible mission force. Ethan Hunt. You guys might know what you're talking about. It was a television show in the 70s. In the 90s, and now it made like 600. Okay, so during the war, you saw it. I still watch it. In the 80s. Yeah. You weren't even made like all that. How big? The only last for men. Women, you were made at your mom. Yeah, we can picture it out. Your mom was born in that. What was your mom? What was your mom? That's you were made with your mom. You were matured. That's the picture you want to you're like
On this line.
She's not agree.
So like, have a solid or
But down there you are. Can you see above the bar? That's where this is where we have contentious relationships. Not if it is agreed chemistry stuff. ETOH, which is something different, right? Logan drinks with you. Can't have a beer or something. That's terrible. Oh yeah. You're really fired. You're really fired. Don't you have a building by yourself? You can keep having jokes about it. It's just a problem. Think about a pot of water. We have a pot of water. I'm trying. So it's not about like I don't it's a trend.
All right, let's hear from different voices. And when I said you can only answer one question, I meant like in this setting. I didn't mean like you're not allowed to ask questions of the facilitators. Please ask as many questions as you want. Just want to make sure that you're not misinterpreting that as like, you must not talk, only one question per day. All right, so I want to hear from different voices, and we're going to kind of go through these pretty quick, through each individual question, make sure we're all on the same page. So can I have lots of hands raised individually for question number 1? At the start of heating of the sample, approximately what temperature is it? Go ahead. Madeline, right? Madison, sorry. -50. Yeah, fine, close enough. It doesn't have to be exact. I'm just trying to say it's starting below 0, starting somewhere -50, and then we're doing something to it. All right? Are the molecules moving? And if so, how do we describe that? Christina?
I would say yes, they are, but they're more of like shaking.
Great. And so a lot of people think of a solid as like, if you want to ask someone on the street, like, are molecules moving in a solid? The most common answer would be no. But hopefully you guys are starting to have a molecular perspective and vision of what happens in molecules in different samples. So there's a lot of vibration going on here. Is there ever a point at which that stops? So absolute 0 is by definition the point at which every movement stops. We have never gotten to absolute 0. We've gotten very close. I think we've gotten down like 0.4 Kelvin in like some really extreme experimental setups. So everything stops moving. All right, so molecules are moving, they are vibrating, and then question number 3, as you use heat and keep adding heat to the sample, right? We're going right, which means we go up the little curve here, or straight line. What if anything happens to the movement of the molecules as we're heating it up, Sarah?
They start shaking faster.
Okay, so it's shaking or vibrating, whatever happens more vigorously. What about, what happens to the temperature as we're doing this? All right, don't need to have a separate answer for that. Temperature keeps increasing as we're adding heat. What happens to the temperature when we get to 0? And maybe we'll combine that with the next one. Go ahead, Avery.
I'd say the temperature becomes stagnant because more energy is required to have the molecules change states, so to go from solid to liquid. So less energy is available to increase the temperature. And then molecules that gain the energy are able to change states.
So the really big picture version of what I want you seeing in your head is that vibration. On the left side, we have all solid. As we add heat, all that solid gets converted from vibrating to now they're moving past each other. Translation is what we call it in chemistry, when something moves in space, moves to another location. You might have seen that in your book. So on the far left side, everything's vibrating vigorously. On the far right side, everything's actually moving around, moving past each other. And that heat, all of that heat that was added, did not change the temperature one bit, at all. And so does anyone know what that heat added to change phases from solid to liquid is called? Heat of vaporization. All right, delta H vaporization is the way you might have seen it.
Isn't the vaporization of the liquid?
Sorry.
Fusion.
Heat of fusion. Sorry.
Yeah.
Thanks, David. I'm going to say that I messed that one up just as much as you by saying yes. And it's interesting that we call it the heat of fusion, because fusion is things coming together, which is one of the directions of it, right? So heat of fusion is, in my head, I think of it as backwards, but whatever. We can tell if it's an input or output of energy. All these descriptions we're having are exactly the opposite when we cool things down. Same things happen, just in the opposite direction. All right. Once a sample becomes a liquid, how do we describe the movement? And then how does that change as we keep adding heat to that? Another volunteer. Anyone? Wait, you've already had one. New voice.
You said you actually.
Brianna?
They're just moving faster. They're moving in space more quickly and farther apart. They're starting to move.
What do you mean by further apart?
Like, instead of being condensed like in a solid, the molecules move in space.
So let's think about water. If we have a block of ice, or let's say a frozen water bottle, and we melt it, does that water take up more space afterwards?
It's more dense afterwards.
So water's a really weird one, and actually does the opposite. It actually contracts when we melt it, which is why if we freeze our pipes in the winter, they expand and they burst copper pipes. It is very rare, and that's because it has such strong intermolecular forces that they actually want to line up perfectly and give space in between them. So if we take, anyone like some water? Anyone thirsty? Sorry, I just poured it out. All right, so when water is moving quickly, it slides past one another. When water slows down, 1, 2, 3, 4, 5, 6, they form these really, really nice little 6-membered rings where we have a hydrogen bond between each of the water molecules, and then each one of those then has another one that's attached to, right? So these is a magnetic version of intermolecular forces. But if water starts moving faster, we don't have that space in the middle. They end up moving past each other, and they take up less space because they're not as slow, and they don't reuse and kind of like, they don't pop into that really nice and organized manner. So that's maybe what it would look like more as liquid, obviously moving past one another. And then as a solid, you end up with kind of what we had before, which was something where there's space in between it. All right. So where are we at? So the part I really agree with what Brianna said is that the molecules start moving faster and faster. One of the best descriptions I have of thinking about this is that molecules, when they're moving past each other as liquid, I think of a pool table and thinking of the pool balls moving past each other. Maybe you'd have to have a lot of them in order to think about it as a liquid because they are touching each other, right, as they move past each other. Maybe a little bit more like gas, the way they're spread out. Are all of those molecules moving at the same speed? Talk to your neighbor about that for a second. At any particular temperature, are all those molecules moving at the same speed? Raise your hands for yes, they're all moving at the same speed.
In a liquid?
Are all the molecules moving at the same speed at any particular temperature? Are they all moving at different speeds? Okay, peer pressure, if nothing else, you'll raise your hand for the second one. So just like if you look at a pool table with billiard balls that are moving around, all of those different water molecules, for instance, are going to be moving at various speeds. Some of them are standing still at any point in time. Some of them are moving really fast at any point in time. But the average speed, what happens at the average speed as we warm up the sample of water? The average speed gets faster and faster. Okay, so that kind of talks about number 8. As we heat up the sample, until it reaches 100 degrees, what if anything changes in the movement of the molecules? They all start moving faster. And one of the reasons that exam practice thing I put up there earlier is really interesting is because if you go through that, a lot of people, when they have a sample heating up, they want to put it keeps expanding and expanding and expanding. And that's one of the biggest pitfalls of thinking about having a liquid warm up, is that if you think about a glass of water, if you have it at room temperature versus if you warm it up to body temperature, it doesn't take up any more space. Very, 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 very little. And we'll actually talk about that as an exception in a minute, but it's like fractions of a percent change in volume. It's not like it just expands. Gases expand if you heat them up. All right, what happens to the temperature if you keep adding heat and you get to 100 degrees? New voice. Get to 100 degrees.
Stops rising.
Stops what?
Stops rising.
Temperature stops rising, and what happens to the molecules, interactions between them?
We start spreading apart the bonds between the molecules.
What bonds between the molecules? What do you call those, maybe more specifically?
Intermolecular force.
Great. And so there's a terminology that I really like to use that's not breaking the bonds between molecules because it makes you think they're covalent. So in biology it would be fine. It's the normal terminology. I'm not saying that to insult people. I'm just saying that's the normal terminology. In chemistry, we really like to say the bonds are being disrupted. The intermolecular forces, rather, are being disrupted. And so now instead of that energy going into raising the temperature, the energy goes into moving those molecules further away from each other and overcoming that intermolecular force. All right, question number 10. Once the sample becomes 100 degrees, how are those molecules moving? Volunteer, volunteer, volunteer. Celia? Sorry, can you get a little loud? Great, so huge thing is they're much further apart, and what about their speed? A lot faster. All right, so there is a fantastic simulation that I think I have linked on one of these things here that goes through all these different steps and looks at how those intermolecular forces change during each one of those stages of heating. So let's look at the flat lines. Question number 11. We have a flat line here. We have a flat line here. If you haven't done it already, talk to your neighbors. Why is the flat line so much longer when going from a liquid to a gas than going from a solid to a liquid? Take about 1 minute to discuss that, and then we will discuss that as a class.
Why does it take something right? One of those.
One of them knows but I was still understanding. Yeah.
All right, so I want to hear you guys' thoughts. Why is one of those lines much longer than the other? It sounds like Logan really wants to answer this one from his group. Go ahead.
Alright, so what we said was the reason that the liquid to gas is so much longer is because in that phase they're actually breaking the intermolecular forces.
They're what, the intermolecular forces?
They're disrupting the intermolecular forces. As opposed to the solid liquid phase when they're not actually disrupting them, they're just letting them move more freely.
Okay, you want to answer that?
Yes, water has a higher specific heat than the solid, so it takes more energy/time to go through a physical change.
True, so mathematically I completely agree with you about specific heat. The underlying reason why is based on the intermolecular forces. So I think that it's really nice to pair those together. It's a really good point. So to summarize what they said is basically that if you think about the before and after going from a solid to a liquid, you still have intermolecular forces between the molecules. Right? They're just now shorter time frame that they have to interact with each other when they're liquid, moving past each other. Interact with this one, then this one, then this one, then this one, right? They're jumping from one to the other. Versus in the solid, they're stationary, and they have four. Every water molecule has 4 hydrogen bonds that it's interacting with. I don't know if I can do a little hydrogen bond. Versus when it goes from a liquid and they're all interacting with something else to afterwards, how many intermolecular forces does each water molecule have after it becomes gas? None. They're spaced apart so far that they don't technically have any intermolecular forces. Now, that's ideal gas description. When one water molecule is bouncing around in the gas and it runs into the liquid, it will then sometimes stick, sometimes not. All right? So to me, there's a lot of intermolecular forces built into a heat curve that I think is really important to kind of wrap our heads around. And that's why I wanted to spend a decent amount of time. Might have spent more time than I wanted on it, but I think it's really important. So then which is, you guys go ahead and label the heat of fusion, delta H of fusion, delta H of vaporization. Go ahead and label those two. Want to label it, Ruby? Now there's two types of diagrams that I want to compare. You guys have maybe worked with this before. Raise your hand if you've worked with a heat curve before. Is this something you've seen in class? Almost everyone's raised their hand. They've seen in some capacity. Hopefully this wasn't totally boring going through it again, thinking about intermolecular force version of it. What pressure does this apply to? Is this at any pressure that this exact figure holds true? Mode?
1 ATM.
Only at 1 ATM. What happens if we take water and we try to do the same experiment, adding heat to it at 30,000 feet elevation? Is the exact same thing going to happen? What's going to change? What decreases? So here, what I like to think about is at the surface of the water, you have all these air molecules that are also coming down and basically bouncing off the top of the water. Some of them dissolve. But they also make it so that if a water molecule is on its way out, it can hit those gas molecules and come back in. If we remove the gas molecules, or 2/3 of them, top of the Everest, you only have 1/3 of the pressure over water that you do at atmospheric pressure, 0.3 atmospheres. And so the boiling point goes way down. It's a lot easier to boil water, requires less heat because there's less gas pushing down on the top of it. All right, so there's another type of diagram called a phase diagram that you guys might have seen. It's the one on the right. What's the big difference? I want you to take a minute, compare and contrast those two diagrams. They're both for water. What do they do differently? So it's just question number 13 that asks about it. So is there any part of these graphs that's the same? Can we get similar information from them? What can we get that's... There's two pieces of information at least we can get that are the same from these two. What are those two?
The temperature of 1 atm. Yeah.
So if we look specifically at 1 atmosphere, and we go across and we increase the temperature, you can see exactly when it goes from being a solid to a liquid, that temperature is 0 degrees Celsius. All right, same thing as over here. This is a little more tech version of the one we were just looking at. Which one of these tells us how much heat it takes to go from a solid to liquid? Both of them? Here we just go over the line, right? Here it tells us exactly how much heat that takes per mole. All right, and then we keep heating it up at 1 atmosphere, and now we boil. Same temperature, right? Boiling point of water. So if we were given a graph and we were asked what molecule is this for, if you knew the boiling and freezing point, if it was either one of these two, you could figure that out. The graph on the left has a lot of information about, surprise, surprise, heat, right? It's a heat curve. So it tells you how much heat it takes to transition, to warm up, all these different things. The one on the right doesn't at all. But the one on the right tells you, well, what if you change the pressure? What does the freezing point and boiling point become at a lower pressure, at a higher pressure? Can we go directly from a solid to a gas? You can for water, it turns out. You can sublimate water, go right from a solid to gas. Carbon dioxide is something you're probably familiar with sublimating. All right, you take dry ice, does it go to liquid ever? It goes right to gas. That's because 1 atmosphere for dry ice is down here. All right, so the components of it, heat of fusion on the left, and on the right, there's no actual value, it just crosses the line. Heat of vaporization on the left and the right. So where on the curve that you guys have would 350 degrees Celsius be? Or sorry, 300, not 350. Where's that? Right here? Okay. So I'm looking at the time, I'm trying to figure out the best use of our time is. I think we should do some discussions about solutions and then come back to the points I had about vapor pressure, just for the people who are doing lab tonight, and actually Tuesday. So let's hold our thoughts on the rest of that. We're going to skip ahead to question number 18. All right. I know that yours aren't red and black. Yours are gray and black, but I think you guys can answer this question either way.
Gray brown.
So go ahead and try to decide which one of these represent a solute, and then check with your neighbor after you've answered this question. And then if you agree or disagree, make sure you can define why you answer that one. All right, can I hear from a new voice? Which one did you answer and why? Austin? Why do you think that red was the solute in this figure? So your definition of solute is?
What gets dissolved in the salt.
That's different than the way you just answered this question.
If there's less of it, then it can be. If there's more, then it could be dissolved in it.
Yeah? It can. So if you think about two liquids, if they're similar in polarity, then one can go into the other. The question is, what do we call the solvent? What do we call the solute? And so for a strict chemical definition, we're going to go by your first definition. The one that there's less of in the mixture is the solute. Do you have a question or you want to add to this? Okay. So the one that there's most of, what do we call that? Solvent. And together, the entire mixture is? All right. How can we describe the relationship between how much of those two there are? Go ahead and write down a list of ways we can describe the relative amount of the solvent solute. What are different metrics we can use to describe that relationship? The ratio or proportion or whatever you want to say. Write down different specific units and how those relate to each other to describe that. Way more. Okay, so let's hear some different ways that you can describe the relationship between the solute, solvent, and maybe solution. Caleb?
The amount of solute in moles over the mass of the solvent in kilograms.
Okay, and what is the formal name for that?
Molality.
Great, so molality is specifically the moles of the solute in the kilograms of the solvent. So specifically between the solute and solvent. What are other ways we can describe it? Logan?
Molarity, moles per liter.
Moles of what per liter of what?
Moles of the solute versus the liters of the solvent.
Okay, so let's actually do so let's even go simpler here for a minute. What are ways we can describe how much solvent there is in this relationship? I heard kilograms already. I heard liters of solvent, or that was liters of solution, right? What are other ways we can describe solvent? What else? So we can do percent, which is kind of a, I don't know where to put that exactly, but yeah. Grams, we can do a fraction between these different ones. What about solute? What are different ways we can describe how much solute we have? Moles, which is how many of them we have. Can we do mass as well? Grams or kilograms or whatever we want. Can we do volume? What about solution? What are ways we can describe how much solution we have? Could describe kilograms as well. We have a percent mass. But what I'm trying to get at here is a lot of students get stuck in this idea of memorizing what different formulas there are for converting between different forms of concentration. All we're saying is, what's the ratio? We can use a number of different ways of describing what they are, but in some way, shape, or form, we're going to be describing how much solute there is in relation to either just the solvent or the whole solution. And so it's going to be some relationship between the moles of solute and the volume of the solution, moles of solute, the kilograms of solvent. We can do mass of the solvent or solute with the mass of the total solution. All these different things are combinations. So try to get out of like the memorization. For today, it's fine if you just write down the way that you convert between these different calculations and examples of that to get through your lab quiz. That's fine. But we're going to be using it, and I want you not to memorize. The less things you can memorize, the more you can just think, oh, it's just the ratio between them, the easier your life's going to be and the more you're actually going to be able to use this after this class. So let's go ahead and look at these two. I want you to describe, what question number is this? question number 20. Which one of these is the solvent? All right, we have 44 responses. Okay, so we're 50-50 on this. Why is it really obvious to say A is right? There's more of it. What did I leave out of the last image, the red and black image?
What types?
What were those dots? What if one of those dots was super heavy compared to the other one? The red was actually 5 times the weight. Then it would have weighed more. But you guys were still right in saying it was a solute. So to define the solute solvent, we have to know how many of them there are, and the one that there's more of is the solvent. So go ahead and figure out how many of each of these there are. You guys know how to do that? And in my class, if you're ever trying to figure out the molar mass, if you know how to calculate the molar mass from the individual atom, just Google it. Don't waste class time calculating the molar mass of isopropanol. Isopropyl alcohol. So go ahead and figure out which one is actually in excess.
It's basically like 46.
Can't answer any.
True. I'm sorry, you did it? I want to see everything written out really nicely.
That is written out really nice.
All right, can I have someone help walk me through how I would answer this question? Lynn, can I ask you to volunteer? So, which is a solvent? How do I figure that out from the information I have here? Say again? So how would we answer this? What are the things we need to calculate? Okay, we need to figure out moles of each of them. So can someone help describe what I do to solve for that?
Alcohol and then divide it by the molar mass of isopropyl alcohol.
Okay, and as you guys probably saw on your worksheet, isopropyl alcohol, I do shorthand. Isopropyl, OH is an alcohol always, so isopropyl alcohol is shorthand. What's the molar mass of isopropyl alcohol? 60.10. Okay, and how many moles do we find that is? 2.36. Okay, and if we do the same thing then for water, What do we find there? 2.2. So which one is in excess? Water is in molar excess, even though those numbers look very different from that. And so really what I'm trying to do is drive home the point that we don't really know how to describe the relationships that we just discussed in the last page if we only look at one of them. There can be very big differences between the different ways of describing this. So let's go ahead and I want you to calculate the mole fraction in this solution of the solute. Calculate the mole fraction. So go ahead and click in the mole fraction of solutes. Mole fraction, mole fraction.
Oh, our sister right here.
Yeah, we're teaching that.
I thought, I was looking at it, it was in the
Well, we all have to go off. Don't do fraction here, so.
Make sure you put in the calculation. Make sure you do work off right. Yeah.
She has my work.
No, I want to see if she has the same answer.
My hair.
So it might ask if you're using volumetric class, maybe it'll ask them online. How do you read the top and this is the bottom? And that's really I don't know. All right, how are we feeling about this? Do we know mole fraction? We have 34 responses right now. So what's a reasonable answer? Whenever we're thinking about mole fraction, what is a reasonable number? New voices, new voices. Trixie.
Less than 1.
Why less than 1?
Because we're putting a part over a whole.
Great. Simple as that, right? All mole fractions are, well, a 1 would be all of it. So how much of that 1 is the solvent or the solute? So it's always going to be a number divided by the whole. And so for this particular one, if we're asking for the solute, the symbol is like a chi. It's a really bad chi. So it looks like a big capital X. It's kind of curvy. And if we're looking for the solute, it'll kind of be written like this. So I totally forgot my numbers now. What is the moles of isopropyl? 3 moles of isopropyl alcohol out of, what's the total number of moles of everything? Is that right? 2.36. I don't know. Okay. If I had calculated that number, how would I have known immediately that it was wrong? It wasn't more than 1. It was 3 over 5. It would have been more than 0.5. Why does that tell me it was wrong?
Because there would be, then it would have been the solvent.
It would have been the solvent. The solvent has more than 0.5. It has more than 50% of stuff. And actually, if you have multiple solutes, it might not even need to be over 0.5 to be the solvent. because the solvent is the one in molar excess. If we have 4 different components, it's the one that there's the most of. Most of the time, we talk about a solution of water, there's usually about 1 billion times more water than the things in it, or at least 100 times more. There's usually a lot more of the thing than there is the solvent itself. So it should usually be pretty obvious. This is a kind of extreme example. All right, so we got, what is this, 0.14? That is the mole fraction. If we wanted to say what is the mole percent, it's not really a thing, but if we wanted to, what percent of the moles would be of the solvent? So we'd multiply this by 100, 42.3% of all the moles are the solute. All right, now it's the mole fraction of the solvent. Go ahead, and if you haven't already written that down, write it down, and then I want to know how we get it most quickly. 30 seconds. What's the mole fraction of the solvent? All right, I hear a lot of people kind of saying it out loud. Can I have one volunteer to say the quickest way to find the mole fraction of the second component if there's only 2? Kayla. Great. So we know 1 is the total. We minus the mole fraction of the solute. We end up with the mole fraction of the solvent. That's it. Okay? Can we answer this if we don't know the molar mass? We start with grams, we don't know the molar mass, we can't answer it. If we start with moles, we can. All right, so you just need to think about what conversions you might need to do in order to answer a question. All right, we have about 5 minutes of class left. So what I want us to do now is, that is that question. I have all this written out here just so you can see it if you want to go back to the slides. I want you now to calculate the molality of this particular solution here. And then after you do that, I think the last one is calculate the molarity of it. These are the last 2 questions we have. Please raise your hand if you're stuck. You can always Google things quickly if you need to move forward. You don't have one of us.
That's CACL2.
That wasn't for my hand. I think maybe it's supposed to be, that's not why it is.
Main reason why I do it in color is so I can see it.
We are running a little bit low on time, so it looks like most people are starting to write things down. All right, let's use the last 3 minutes effectively. Honestly, the most important thing in trying to answer these questions expediently is making sure that you know what that little m means. What does that little m mean? Molality. It's really hard to say when it's a 1 molal solution. Molal, I hate saying that. So how do we, the first thing to start is what are the units going to be in order to use that description of the ratio between the stuff and the solution? So we're going to do moles, and we're going to be more specific. Solute in, are we doing solution or solvent now? And what unit? Mass, volume? And it's specifically the solvent. So do we have either of these? Do we have the kilograms or the solvent? Close. We have the grams, and so we can convert between that pretty easily. What about moles of our solute? Find that, right? So we can go directly from 32.0 grams of calcium chloride. We can do the molar mass conversion, and we have moles of solute. And then our kilograms, 0.271 kilograms of water. All right, you can show the conversion if you want for that. What about doing molarity? Is that easier or harder? What's different? Is it the exact same thing we have there? So what's the biggest difference? All right, so now it gets a little bit challenging. Because now we have to say, well, what's the volume? We don't have volume anywhere in there, right? How do we get from this information to the volume of the solute? Well, if we had the mass of the solution, we could probably use the density, but we don't have the mass of the solution, do we? Can we find the mass of the solution? Mass of the solution. We know how much of the solute. We know how much of the solvent. The total is the mass of the solution. And then we have this really nice conversion factor that's the density. We know exactly how to convert. We have 0.752 grams. We know that is 1 milliliter, which is a form of volume. So really what we want to think about whenever we're doing our calculations with concentration is what unit do we have of the solvent or of the solution? Do we have the moles? If not, how do we get there? Density is going to be the one most challenging component, is using density to convert from mass to volume. All right, thanks for your patience, guys. You're a minute over. So feel free to come down if you have any more questions.